Okay, we've seen how linear constant coefficient equations are derived and come up in practice. We're going to focus now on finding solutions to these things. In particular, we're going to look at the special case. We have a constant coefficient linear homogeneous equation, so that's a lot. And it's going to be higher order differential equation. So what does all that mean? When we say constant coefficient, we mean that everything in front of the a's, or in front of the dependent variables is a constant. So a, b, c is a constant in this case. It's linear in that it's just x double prime, and x by itself. And it's homogeneous because there's a zero. There's no explicit mention of the independent variable anywhere. And it's higher order because the number of derivatives is greater than or equal to 2. And we're going to be able to generalize this to the case where we have 3, 4, 5 on up. And in particular, what's going to happen is we're going to make a guess. And when we make that guess, three different things can happen. And we're going to have to look at each of these cases separately. And for now, we're going to be focused on the case where everything works out nice. And then we're going to go back later and sweep up the cases where things break down. In particular, we're going to not just focus on second, but also third, fourth, and higher order equations. So if we have n derivatives, to undo that, you can think about taking n antiderivatives. And we're going to need to take n derivatives, and we're going to have n unknowns, or n constants. So in the end, if we have however many derivatives we have here, we should have that same number of constants floating around. And if it doesn't work, then we've done something terribly wrong, or things have gone horribly wrong. So let's just focus now on the second order, and we'll find out that what we do for the second order case is going to be generalized to the third, fourth, and higher order cases. So what is it we're working with? We have an equation in this form. We're going to make a guess. If the guess works, then we're done. If the guess does not work, then we're not done, and we have to go over and start something different. What's going to be important here is to recognize when things work, but also when things are not working. And if things are not working, you have to go back and do something else and try again. So what's the idea is we have our function x. We're going to take a derivative, and then we're going to take a second derivative and plug it back into the equation. And when we plug it back into the equation, everything has to add up to 0. So here we have c times x, b times x prime, and a times x double prime. When I add all those things up, everything has to cancel out, and I'm left with 0. And so the question then becomes, what kind of functions, when I plug into here, basically look like themselves and allow us to cancel things out? Well, the first thing you might look at and notice is that if I take derivatives of cosines and sines, I'm going to get cosines and sines back. So this seems like a pretty good candidate. Another good candidate is going to be an exponential. Now, if I take a derivative of an exponential, I get another exponential back, and I expect to knock things out. Notice, though, because of Euler's formula, that means then if I get an exponential and I get a complex number, I can deal with this and turn it into cosines and sines. So it's going to turn out that an exponential of this form is going to be more general case, and it's going to be able to deal with cosines and sines. So we're going to try this first, and if it works, then it works. Okay? So what's the idea? The idea then is that if I have something of this form, and again, A, B, and C are constants, I'm going to try the most general exponential I can. I'm going to rewrite that because that was messy. So think of it as rent. So R is a constant, N is a constant, and I don't know what they are. I'm going to specify them later. I do know what A, B, and C are. Those are constants that are given to me. If I can figure out what values of R and N make things work, then I'm done. So what's going to happen here? So my x of t is RE to the nt. My derivative, well, the derivative of an exponential is the exponential times the derivative of what goes in the exponential. So I'm going to get RE to the nt times n. If I take a second derivative of that, it's going to be the same thing. I'm going to have RE to the nt times n. N's a constant. If I could take another derivative of nt, so I'm going to get RE to the nt n squared. And I'm going to plug these back into my differential equations. So multiply that by c, that by b, and that by a, and add. So if I add all those things up, so ax double prime plus bx prime plus cx has to be 0. Then a times x double prime, that's going to be RE to the nt n squared, plus b times x prime is RE to the nt times n, and then c times x is RE to the nt is 0. Every term has r times e to the nt, so I can factor that out. If I do that, I'm left with an squared plus bn plus c is 0. Now I have three options. Either r is 0, e to the nt is 0, or this whole big thing, bn plus c is 0. I don't want r to be 0. If r is 0, that says x is 0, and that's not a solution. Exponential can't be 0. It's always got to be non-negative. So that can't be true. So I'm left with that. So if I have an squared plus bn plus c equals 0, life is good. Now, this is second order, so I need to have two solutions. So there's going to be three cases. The first is I'm going to have two distinct solutions. I'm going to have two different values of n that satisfy this. And if I do that, I'm going to basically have RE to the n1t plus R2 e to the n2t is going to be a solution. Case 2 is there's a double root or one solution. I'm going to come back. We're going to deal with that later. That's too much for now. In case 3 is I'm going to have two complex roots. We're going to deal with that later, but it's going to turn out to be not a big deal. And it's not going to be a big deal because I already have Euler's formula and I can just do it. All right. So, what's going to happen here? At this point, we're going to focus on case 1, where we're going to have two solutions to this quadratic equation. And if I have two solutions, that means that is 0 and that is 0, and n1 is not equal to n2. Right, so we started with an squared plus bn plus c is 0. Notice it's quadratic, so I can use a quadratic equation. And if b squared minus 4ac is greater than 0, I have two solutions, n1 and n2, no big deal. If b squared minus 4ac is equal to 0, I'm going to have one solution, or a double root. I'm going to have to come back to that. So that's case 1, 2, and then case 3. If b squared minus 4ac is less than 0, I'm going to have two complex roots. And then I'm going to use Euler's formula to deal with that. All right. So my claim is for case 1, my solution is going to be the sum of those two things, r1 e to the n1t plus r2 e to the n2t. And I'm going to use the fact that they both solve the same quadratic equation to show that this thing is a solution. By the way, in terms of nomenclature, I can say a general solution. That is the situation where we have no initial conditions. If you have initial conditions, and in this case, because there's two unknowns, we need to have two pieces of information, we'll find the solution, and that will be the particular solution. These are two different things, and you should read the question very carefully to decide what you need to work with. Okay, so my claim is if I have the second order differential equation and it has two roots to this quadratic, then the sum of these two exponential functions is a general solution to the original differential equation. And the reason is, if I take derivatives and plug it back in, so the derivative of the first term is r1 e to the n1t times n1. Derivative of the second term is r2 e to the n2t times n2. And the derivative of the second derivative of the first term is going to give me an n1 squared. Second derivative of the second term is going to give me an n2 squared. When I plug this back into the equation, so a times x double prime plus b times x prime plus c times x now I can distribute the a to both of those terms. I can distribute the b for the first derivative term. And distribute the c for the x term. So that's n1t plus c r2 e to the n2t. Now notice I can add the exponential terms that have e to the n1t, and I can separately add the exponential terms that have e to the n2t. If I do that, notice I've got r e to the n1t, r e to the n1t, r1 e to the n1t, so I can factor that out. I have a n1 squared plus b n1 plus c. Then for this term, notice I've got r2 e to the n2t, r2 e to the n2t, r2 to the n2t. I can factor that out, and I'm left with a n2 squared plus b n2 plus c. But I already know that a n1 squared plus b n1 plus c is 0, because that has how I defined n1. And n2 is also a solution to the quadratic equation. So the whole thing is 0, which means then that when I take that equation and plug it into my differential equation, it equals 0, and it is a solution.